Hi, Astronomy. Mr. Janowski here. This is the first part of the Chapter 5 slides. So this chapter is about telescopes. So tele means at a distance and scope means seeing. So astronomers can't actively probe the objects they want to study. I've said this before, I'll say it again many times. If you're an astronomer and you're trying to study a star, you don't have the option of flying up to that star, taking a big scoop of it, and bringing it back to your lab at home. You can't do that. You have to just sit back on Earth, or sometimes with a space satellite, um, and passively collect the light from the star. So the light's going to come to you. You're just going to collect it. So the objects we're going to be looking at are often so remote that their light is very, very faint when it gets to us, which requires the use of big, big telescopes. So the two in this picture, these are the twin Keck, blah. These are the twin Keck telescopes on Mauna Kea in Hawaii. So Hawaii, up on top of the mountains, you can see the snow there, ends up being a very good place to do astronomy. So if you were to try to read a newspaper from all the way across a dimly lit room, you would not be successful for two reasons. One is there's not enough light to see the letters. And two, even if there were enough light, even if you turn the lights on, you can't make out that small a resolution from that far away. You don't have enough resolving power. So these are the two things that telescopes do for us. They give us more light gathering power, and they give us more resolving power. Now, notice I didn't put they magnify things on this list. They do, in fact, magnify things, but that's not really enough. Magnifying something without having enough resolving power doesn't help you. So it's really resolving power that's more important than magnification, and also light gathering power. So when you see something with your eye, photons enter your eye. They're all the different parts of the eye. Mrs. Keller can tell you all about them. But for us, the important thing is the pupil. So this is the black part in the middle of the colored part of your eye. Just the black part right there. That's where the light gets in. And it goes in. Your whole eye is a lens, but there is a part of your eye specifically called the lens. It gets focused on the retina at the back. This is basically the screen that senses the light and converts it into a signal that goes to your brain, and your brain turns it into your sense of vision, basically. Anyhow, the diameter of your pupil in dim light is going to be about 8 millimeters, so 0.008 meters. So if you have a circle with that diameter, what is the area of that circle? The formula for the area of a circle is pi r squared. So this formula is going to be important. This is how we figure out the light gathering power of a telescope, is by looking at its radius, plugging it into this, getting the area of the telescope, and that's basically its light gathering power. Anyhow, in this case, you plug in 4 millimeters, 0.004 meters, because if that's the diameter, this is the radius, into this formula, and you get this really tiny number, 0.0000503 meters squared. The area of your pupil in units of square meters, it's just tiny. If you could think of a square that was 1 meter on a side, that'd be a reasonably big square, way bigger than just the black part of your eye. So that's why it's this tiny number. Now compare this to a large telescope. So not the kind of telescope you might buy, for your birthday, but a large telescope that they might use at a, professional observatory. So that telescope might have a diameter of 8 meters. So plug that 4-meter radius into this formula, and you get an area not of 0.00005 meters squared. You get 50 meters squared, which means that telescope has literally 1,000,000 times the light gathering area of the pupil of your eye. So it's got way more light gathering power. So notice that the area of a circle is proportional to the radius squared. So that means when your telescope triples in radius, it actually gets 9 times the light gathering power. Because if the radius is 3 times as big, then the area is 9 times as big. So yeah, making a big telescope lets you collect a lot more light. So astronomers can use a telescope to collect more photons and then funnel, in scare quotes, them down to a certain point to make an image. So here's a small telescope, still way bigger, light gathering area than the pupil of your eye. But this small telescope will give you a fairly dim image. If you look at the same part of the sky with a much bigger telescope with much more light gathering power, you're going to get a much brighter image. So once the light has been gathered, it must be focused to form an image. So you can focus it with a lens. That's one way to do it. So light beams coming in here, they get focused down here. You can make an image this way. Now, telescopes in which the light is gathered and focused by a lens are called refracting telescopes, or refractors for short, because they use refraction, is the optical phenomenon that makes this work. So this is something we learned about in last chapter. When you have light going from one medium to another, so in this case, in the case of a lens, it's going from the medium of the air to the medium of glass, and it hits it at an angle, then it's going to change speed, and that causes it to change direction. That's what refraction is. So lenses have serious disadvantages when you're making a telescope. So one is that large lenses are extremely difficult and expensive to manufacture. To make a really big piece of glass, like a meter in diameter, it's really hard to do that. And it's really expensive, and it's hard to get it right. Another thing is your lens must be supported at the edges so as not to block the light block the light gathering area. So if you have a lens like this, imagine this thing kind of pointed upwards towards the sky, not sideways like this. You've got to support this thing at the edges, because if you support it in the middle, you're just blocking the light gathering ability of the telescope, and that's kind of the whole point. So that's not a good thing. A very big, heavy piece of glass is going to want to sag. So if you're supporting it only at the edges, it's going to bend a little bit. It's going to dip. It's not going to be the right shape anymore. So that's not good. Now, lenses have dispersion, which we learned about last chapter, meaning the different wavelengths of light are going to be bent by different amounts. They're going to spread out. They're not going to come to the same focal point, and you get what's called chromatic aberration. So here is, the cover of Dark Side of the Moon. You've got white light coming in at an angle, so it refracts right here. But because the different wavelengths and the different colors refract by different amounts, they start to spread out, and then they refract again over here. So now they spread out even more. And this gives you the wonderful, very beautiful effect of, what a prism does, which is great if that's what you're going for. But if you're trying to make a sharp image, this is the opposite of what you want. You don't want this. And that gives you chromatic aberration. More on that on the next slide. And the final thing is that lenses absorb short wavelength light. So UV, X-rays, that kind of light, meaning you can't use them to do some types of astronomy, because if that's the light you're interested in and your lens is actually eating that light and blocking it, not letting it go through, well, you can't do astronomy with that. So here is chromatic aberration, which is a fancy way of saying color fringing, which is a defect that you get in lenses. So really expensive photographic lenses, they combine different pieces of glass in very clever ways, and they try to minimize this effect, but you can't minimize it perfectly, even doing that. But yeah, so this picture kind of shows you what's going on. Because your different wavelengths are being bent by different amounts when they go from one medium to the other, here and here, they don't come to the same focal point, which is what you want them to do. So they spread out a little bit, and you get weird color fringing. So here is that kind of color fringing. I know from knowing photography that you can see this kind of thing most when you have a light area next to a dark area. So the bright light of the flower next to the dark green of the background, this is where the fringing is going to be most apparent. So this, bluish purple bit here, that's an imaging artifact. That's not really there. It's just a limitation of your lens, and you don't want that. So that's a bad thing. So lens is bad for making a telescope. So the 40-inch, 102 centimeter, 1.02 meter diameter telescope at the University of Chicago's Yerkes Observatory was completed in 1897 and is, to this day, the world's largest refracting telescope. So, this telescope is obviously many, many meters long, but the, 1.02 meter, that's the diameter of the lens. I don't know if the lens is at the very end of the telescope, but, it's somewhere along the length of this telescope is the lens. And that's the biggest one of these telescopes we ever made, and we made it in 1897. So 123 plus years ago, 124. It's only February. That's when this was completed, and we haven't made a bigger one of this type since, because we realized this isn't the best way to make a telescope. Here's Albert Einstein, by the way, visiting the telescope. He didn't work there. So because lenses have those limitations, most modern telescopes, the large ones, are going to use mirrors instead of lenses. So if they're using mirrors, they're reflecting the light, and we call these reflectors or reflecting telescopes. So mirrors are made of glass that has been shaped to a smooth curve, a very precisely, very carefully ground, really damn near perfectly shaped piece of glass. Shaped that way, polished very carefully, and then coated with a thin layer of aluminum or some other highly reflective material. So here's this is the Large Binocular Telescope, I think is what this one's called, in Arizona. So here are the two big mirrors. Now, let me point out the mirror you have in your bathroom, it has the glass on the front, and it has this, the silvered part, which is, probably aluminum, on the back. That is so that if you get a fingerprint on it, you can clean it and not wipe away the aluminum that's making it reflective. So that's the way, that kind of mirror works. The mirror in a telescope is going to be flipped over from that. So you're actually going to have the glass part on the back, and the part that does all the work, the reflecting part, is going to be the aluminum coating on, basically the front side of this. So that is optically much better, but it also makes the thing very, very delicate. You can't touch this kind of mirror, because if you do that, you're just going to take the aluminum coating right off. So mirrors have many advantages over lenses. One is they are relatively easier and less expensive to manufacture than lenses are. It's still really, really challenging to make a giant mirror like this and make it optically really, really precise. But it's relatively easier compared to trying to make a giant lens. Now, because the light does not pass through the mirror, you can support the mirror from behind. So remember when I'll zoom back many slides, when you had your big lens, you had to support it at the edges, because if you block it in the middle, you're not letting the light get through. Well, jump ahead to this guy. You can support this anywhere you want. So you're going to have supports all the way along the back of this thing, because light doesn't need to go through it. That's not the way this thing works. So that means you can make a much bigger and heavier mirror and not have to worry about sagging, because you can support it everywhere. It's not exactly that you're not worried about it. More on that on the next slide. But you can eliminate the sagging by doing it that way. Now, light doesn't pass through the glass part of a telescope mirror, so you don't get any dispersion. All the reflecting happens on this aluminum part, so none of it's going through any glass. So you don't have that, prism effect with the light spreading out, the different wavelengths spreading out. So no dispersion at all. And finally, the mirrors don't absorb the short wavelength light, because none of the light is going through any of the glass. It's all reflecting off of the aluminum. So you don't have that problem either. So mirrors win on all four counts here. So back to the second point here. Because the light doesn't pass through the mirror, you can support it from behind. So this is a giant mirror here being supported from behind. So all of these little guys here, these are all different arms, all controlled by, I'm guessing M stands for motor in this case, supporting these little arms that are going to push the arms up and, pull them down, whatever they need to do to correct for any sagging that this mirror is going to do under its own enormous weight. So some of these mirrors can weigh, 10 or 20 tons. They're huge. So they want to sag, but you just support it from behind and control it with these arms and keep it from sagging. So the little arms that do this technology is called active optics. So there are a few different technologies you're going to learn about telescopes in this chapter. The first one we get to is active optics. So this refers to the corrections made to the shape of the primary mirror. That's the big mirror, the main one. Also primary, it's the first one. To prevent it from sagging under its own weight as it is repositioned. So as you tilt this thing all around, all over, all across the sky and tilt it up, tilt it down, it's going to want to sag in different ways. So you need to keep adjusting these things. But these corrections are made relatively slowly as compared to the adaptive optics corrections, but that's way later in this chapter. So yes, that is active optics. That's what these little arms are, supporting the mirror from sagging. So here is our large binocular telescope on Mount Graham in Arizona. It has the largest non-segmented mirror of any optical telescope. So non-segmented. Each of these mirrors is one giant piece of glass. More on that in a couple of slides. So these two giant mirrors together, each mirror is 8.4 meters in diameter. They have the light gathering power of a single 11.8 meter mirror. So if you took the area of two 8.4 meter circles, you would have the same area as one 11.8 meter circle. That's what's happening. And are capable of the same detail as a 22.8 meter one. So that probably doesn't make a whole lot of sense at this point. That'll have to do with another technology called interferometry, which we'll get to later. But yeah. So large binocular telescope, big mirrors, each one of which is a single large mirror. So there are different things you can do. There are different basic designs of these reflecting telescopes. So the light comes in, it's reflected, and then different things are going to happen. So one type is called a prime focus telescope, in which case the light reflects and then it's focused here and you make your image right here. So that is one type. The other types are going to use secondary mirrors, and they're going to deflect the light in a couple of different ways. So one way is called a Cassegrain focused telescope. So the light comes in here, hits the big primary mirror, just like in the other type. It comes back here, but now it hits the secondary mirror, and it gets redirected through a little donut hole in the middle, and you make your image down here. And you might have an eyepiece, or you might have a camera, or some other instrument down here. So that's how that works. And yes, doing it this way does block a little bit of the light, but it ends up not being a huge part, so it's still worth doing it this way. So that is a Cassegrain focus uh, kind of telescope. The other type, the light comes in, hits the primary mirror, goes back up to a secondary mirror, but instead of being sent back down through the donut hole, it is just shot out through the side, and you make your image over here. So this is called a Newtonian focus telescope because Newton, I don't know if he actually invented this type, but he made a very good one, or a very good early one at least. So that's Newtonian focus. So to help you remember, imagine that this guy right here is Isaac Newton. Now, let me point out something. If you decided that you wanted to buy a telescope for yourself, um, if you bought a cheap one, it would be a refractor. It would work with lenses. It wouldn't be this big, as big as the one they have at Yerkes Observatory, but it would use lenses. It would be a refractor. If you wanted to spend a few $100s up to a few $1,000s, you would get one of these. It would end up being a Newtonian focus one. This is like the most popular design for the kinds that astronomy enthusiasts buy for themselves. Now, the big, like the really serious ones they have at observatories are going to be some variation of this Cassegrain focus one. So they won't be Newtonian. They'll be Cassegrain or some variation of this. So which ones are the prime focus ones? Well, according to this, you can actually make your image right here. I've never seen even an image of an optical telescope that actually works that way. But this is the way radio telescopes work. Light comes in, hits the radio dish, goes back up, and it's all collected and imaged up here, is how a radio one works. So radio telescopes, prime focus. The one you might buy for yourself, Newtonian focus, or refractor, if you're going to cheap out. The main big ones we're going to look at are going to be Cassegrain focus telescopes. So now we're making our image. Now remember, back in chapter 1, we learned that the Earth rotates, and that makes it look like the celestial sphere is rotating above us. So you end up with these big star trails across the sky. So if you just locked your telescope in place, pointed it at the sky, and made a long exposure, this is what you would get. And this is a very neat effect, but it's a useless image as far as astronomy goes. You can't analyze the things that are in here. So instead of just locking your telescope in place, your telescope actually moves. So as your thing is moving across the celestial sphere, or appearing to move across the celestial sphere, the telescope's going to follow it. It's going to move with it. So I don't know if these are Keck. I think they're Keck. These are the two twin ones at Keck, I think, in Hawaii. So notice these guys are moving. Not only are the telescopes moving, but the whole building is moving too. So these things have to rotate to follow the thing. And the yellow lines coming out of them, those are actually lasers pointing up at the sky. This is related to adaptive optics, which is a technology we'll get to later in the chapter. So yeah, the whole thing's move. Now, getting many tons of metal and glass to move smoothly with great precision and without changing shape, because if these things are rattling all over the place, you don't want your mirrors to be, warped or anything like that, is very technically demanding. So modern telescopes are designed with thin mirrors and sophisticated alignment systems supporting them from behind. That's the active optics part. So another thing they do is they use, this is another technology telescopes use, multi-mirror instruments. So the large binocular telescope, that was two non-segmented mirrors. Those were just single large pieces of glass. And we kind of stopped doing it that way, at least, for the most part. So the biggest ones we're making now, instead of having one giant mirror, they have all these honeycomb hexagon shapes, and they put them all together and they get them in the right shape. And you can make it, effectively one bigger mirror this way by making it out of many smaller mirrors. So this is the 10-meter segmented mirror in one of the twin Keck observatory telescopes. So yeah, multi-mirror instruments, that's another one of your technologies. Now, the largest such mirror currently in use is the 10.4 meter diameter mirror at the Gran Telescopio Canarias, the Gran TCAN, in the Canary Islands. So it's mostly run by Spain. It's actually off the west coast of Africa, the Canary Islands here. So this is the largest such one in the world. But they're building a bigger one. In the Atacama Desert in Chile down here, they're building the ELT, the Extremely Large Telescope, or the EELT, the European Extremely Large Telescope. So the biggest one we have now, 10.4 meter diameter. The one they're building, and hopefully will be up and running, they call it, we'll see its first light in 2024. They're building it down there in Chile, 39.3 meters. So that's a big jump. 10.4 meters squared is something like 100 square meters. 39 meters squared, close to 40 meters squared, like 1,600 meters. So yeah, that's a big improvement. So that's the ELT. I love the name of this, the Extremely Large Telescope. Now they actually designed an even bigger one, the 100 meter diameter OWL for Overwhelmingly Large Telescope. What a funny name. But they're not actually building this one, because they decided this one would be too difficult to make. They could make it, maybe, but it would be really expensive, and they couldn't be 100% sure that the damn thing would actually work. So instead of making one of these guys, they're making this guy instead. So these are some of the different telescopes. So I'll just point them out quickly. Yeah, this is the Yerkes one, this tiny little blue dot up here. Blah, blah, blah. Hubble is this big, so Hubble's pretty big. The sort of replacement to Hubble is the James Webb, so it's noticeably bigger than Hubble. This one, planned for 2018. Yeah, it didn't happen. Hopefully it launches 2021 or 2022. The Gran TCAN in the Canary Islands, that guy's this big. A little bit bigger by itself than either of the Keck ones. We also looked at the Large Binocular Telescope. These were the big non-segmented ones in Arizona. There's another telescope called the Very Large Telescope, the VLT. So all four of them together is called the VLT. Each individual one, they're called unit telescopes. So there's that. The Giant Magellan Telescope. I'll link to a video for this one. It's a neat one too that's currently being built. What else do we have? 30-meter telescope. They're trying to build this in Hawaii. It's being held up. People are protesting. They don't like the location they're building. That's a long story. I'm not going to get into it. The ELT, or the EELT, the European Extremely Large Telescope, is going to be this big. Now, if they had built the OWL is this giant gray donut in the background. The Overwhelmingly Large Telescope is, simply huge, but they're not going to build that one. So that's a shame. And then finally, if you look at this curve down here, what's suggesting a curve that's going to go up, it'd be a giant circle. That is the size of Arecibo, which was a giant radio telescope that we used for many years. You may have seen it from the movie GoldenEye. It was a James Bond movie. It was in the movie Contact. Arecibo down in Puerto Rico. And it was in the news this year because it had, its big collecting thing up at the top, supported by cables. And the cable started to break, and they were worried about it. And then turns out cables started snapping like crazy, and the basically it collapsed. So that telescope is now ruined. There's no way to repair it. So Arecibo, unfortunately, is all dead. No more Arecibo telescope. So then we watched these two videos in class. How large can a telescope be? The Steep Sky one. We watched at least most of it. And then this other one is neat. This has to do with the Large Magellan Telescope, or the Giant Magellan Telescope, this one here. They show you how they're making the mirrors for that at the University of Arizona. That's one of their specialties, is they make giant telescopes mirrors there. So if you watch this, just the technology going into these things. If you watch these videos, it's amazing. It's crazy how smart and how high tech these things are. It's just it's unreal. And then there's the Kahoot, which we didn't watch at the end of the first class. We'll do the Kahoot at the beginning of the second class. So again, I'll link to these videos, and hopefully you found this helpful.